Yes, good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exams. Okay, we'll be looking at chemistry today, and what we'll be dealing with is gas laws. Um, when we talk about gas laws, in order for us to understand the behavior of gases, for us to know why gases behave the way they do, there are laws that governs that. And in understanding these laws, in understanding gas laws generally, there are four variables that we need for us to describe the physical state or condition of a gas. These four variables are volume, pressure. When we talk about volume, we mean the space. When we talk about volume, we mean the space that a gas occupies. Then when we talk about pressure, you're looking at, okay, let's say this is a vessel and we have gases in this vessel. You need to understand that gases are constantly bombarding the walls of their containing vessel as they hit on the walls and as they collide with one another. Gases constitute what we call vapor pressure, in this case, pressure. And of course, we talk about temperature, more specifically, absolute temperature of gases. And lastly, the amount of gases in moles are the four variables that we need for us to be able to understand the physical state or condition of a gas, or more specifically, the behavior of a gas. When we talk about gas laws usually look at relationship between any of these two variables or more, by the way. So gas laws looks at the relationship between these variables. So we'll be looking at Boyle's law, we'll be looking at Charles's law. Boyle's law talks about pressure and volume relationship. Charles law talks about volume and temperature relationship. And of course, we'll be combining Boyle's law and Charles law to get our general gas equation. We'll be looking at Avogadro's law. We'll be looking at ideal gas equation, of course, looking at real and ideal gases. What are the differences between them? When is it that real gases behave ideally and all of that? We'll be looking at Boyle's law of combining volume, Graham's law of diffusion, that's talking about molecular diffusion. We'll be looking at Dalton's law of partial pressure, and of course, relative vapor density. So these are many more are the things we're going to look at under gas laws. So moving on, the first law we'll be talking about is Boyle's law. Boyle's law talks about volume pressure relationship. So Boyle's law states that the volume of a given mass of a gas is inversely proportional to the pressure, provided that the temperature remains constant. So emphasis on the word volume of a given mass. To say volume of a given mass here talks about number of moles as being constant. Of the Boyle's law states that the volume of a given mass of a gas is inversely proportional to the pressure. When you talk about inverse proportion, it means when one quantity increases, the other decreases, and when one quantity decreases, the other increases. So the volume of a given mass of a gas is inversely proportional to the pressure, provided that the temperature remains constant. What this simply means mathematically is that volume is inversely proportional to the pressure, provided that the temperature remains constant. This will give us V equals to K over P. So the implication of this is that PV equals to K. In this case, the K here means number of moles of gas and the constant temperature. When you look at most gas law looks at the relationship between two variables, keeping the other two variables constant. Remember that we said that in describing the behavior of a gas, these are the four variables that we use in describing the state or the condition of the gas: volume, pressure, temperature, and the amount of gas. So what most gas law looks at is this. It looks at the relationship between two variables. In the case of Boyle's law here, volume is inversely proportional to the pressure. When volume increases, the pressure reduces, and when pressure increases, volume reduces. So keeping temperature and the amount of gas. That's why we said volume of a given mass. To say a given mass here is to talk about the mole, and then the temperature is constant. So PV equals to K. In other words, looking at what we got mathematically here, we can say that the product of pressure and volume of a given mass of gas is constant, provided that the temperature remains constant. So what that means is that since product of pressure and volume is constant, we can say that we can restate Boyle's law as product of pressure and volume of a given mass of gas is constant, provided that the temperature remains constant. And that's exactly what we have here. So that said, looking at this PV equals to K, we can also indicate this. Let this be a containing vessel with a movable piston, okay, such that it could go up and down. Okay, let this be a movable piston containing a certain volume of gas. Let the volume here, let the volume be 50 and cm cube. Okay, let the volume be 50 cm cube, and let the pressure here be 2 atmosphere. Of course, for one reason or the other, if we increase the volume, let's increase the volume of this so that this is the new volume, and now the gas are more spaced out. The moment we increase the volume, it means where a gas could move here, gets here, and constitute what we call pressure. For this gas to travel here now, and then to travel here, and then to travel here. So the pressure here is going to be more. As we've increased the space, as we've increased the volume here, it means it will take longer for the gas to collide with the walls. In other words, when you increase the volume, the spacing, the frequency at which the gas molecules here collides with the wall is going to reduce. Let's say the volume are doubled to 100 cm cube. You're going to have a situation whereby the pressure here would have to about 1 atmosphere. So that by the time you say PV here is going to be 50 times 2, and PV here is going to be 100 times 1. You get the 100 here, you get the 100 here. The implication of this is that P1 V1 equals to P2 V2, and this is exactly what we use for most of our calculations that has to do with Boyle's law. Now, having said that, that's why you have this. Whenever the pressure increases, if this were to be the pressure, whenever the pressure is high, the volume is low. When the pressure reduces, the volume increases, and when the pressure decreases, the volume further increases. That is to tell you that volume and pressure here, that is to tell you that volume and pressure here, they have an inverse relationship. When volume increases, pressure is going to decrease. Pressure is going to decrease. And by the time pressure increases, volume is going to decrease. Also, since we've said volume is inversely proportional to pressure, we need to know that when this is volume, and when volume increases to 2V, when the volume has increased, then if this was the pressure before, what will happen to the pressure is that the pressure is going to halve. If volume was V before, and the volume increases to, let's say, 4V, then what will happen to pressure is that pressure is going to become P over 4. Pressure is going to be divided by a factor of 4. But if we were talking about a decrease, let's say volume had decreased by 2. If the volume is halved, then pressure is going to be doubled. If the volume is divided by a third, then the pressure is going to become 3 P, and like that. Also, we can indicate Boyle's law graphically. Graphically trying to indicate Boyle's law, that's going to be V here in cm cube, and we said it's inversely proportional to the pressure, so we could have 1 over P here and a straight line through the origin. Also, we could have a graph of Boyle's law this way. Let this be the volume and let this be the pressure when you have a line this way. Let's look at it. Imagine this is 5. At the time when the volume was 5, the pressure was, let's say, 1. When the volume had decreased to 4, what had happened to the pressure? The pressure had increased. When the volume had decreased to 3, you can see the pressure had increased to 3. When the volume had decreased to 2, you can see the pressure had increased to 4. So basically, when you have a graph this way and then you have a straight line this way, you know, from the vertical to the horizontal axis, that is an inverse relationship. Also, this will mean a graph of Boyle's law, V, P, a parabolic curve from the right to the left. That's going to mean inverse. Also, you can talk of a graph of Boyle's law this way. Since product of pressure and volume is constant, and this here is a UTME question, you take that very seriously. This is going, your horizontal axis here is going to be pressure. This here, take note of it. This is a very important question. It's a UTME question. So 1, 2, 3, 4. Any of these 4 graphs can be used to represent Boyle's law. So the next thing we're going to look at is to take calculations that relates to Boyle's law. So, okay, moving on, let's look at some calculations that has to do with Boyle's law. The first one says that the volume of a given mass of gas with initial volume 200 cm cube. So it means here that V1 equals to 200 cm cube. When the pressure is increased from 600 millimeter mercury to 800 millimeter mercury, calculate the volume. So we're looking for the final volume here. When the pressure is increased, P1 here is 600 millimeter mercury and P2 here is 800 millimeter mercury. So we're basically looking for V2. Those are the things we can extract from the first question here. Of course, you recall that P1 V1 equals to P2 V2. So I am looking for my V2 here. So if I try to make V2 the subject, so P2 we have to come here. So P1 V1 over P2 equals to V2. Invariably, what I even expect of my answer is that since the pressure had increased, I expect my answer to be less than 200. Those are the predictions. If the pressure had increased from 600 to 800, then volume should decrease according to Boyle's law, so that my V2 equals to my P1 is 600 times my V1 is 200 divided by 800, and I'm going to be getting 150 cm cube for my new volume. That ends question 1. Okay, looking at question 2. A volume of gas at 30 degrees Celsius, okay? The gas was at 30 degrees Celsius, okay, occupies a volume of 48 liters. V1 equals to 48 liters, okay, and exert a pressure of 2 atmosphere at that time. P1 equals to 2 atmosphere pressure. What volume will the gas occupy? So I'm looking for V2 here. What volume will the gas occupy if pressure is changed to 1 atmosphere? P2 equals to 1 atmosphere. Even without solving this, if the pressure had moved from 2 to 1, which means the pressure had halved from 2 to 1 atmosphere, I expect the volume to double. But here we were told that at the same temperature. So which means the temperature before was 30 and now the temperature is still 30 degrees Celsius. It is constant. So for those that think every of the figure you see in the questions, you must always use as a you must always include every of the parameters or every of the values you have in the question. You might be wrong here. In this case, we don't have any need for the 30 degrees Celsius because we were told that the temperature remains constant. So what we have here is that V2, if we use P1, V1 equals to P2, V2, then my V2 is going to be P1, V1 over P2, and that's going to be 2 times 48 divided by 1. I'm going to get 96 liters, and that answers it. If the pressure had halved, then the volume should double. Moving on to the third and final question for Boyle's law. A sample of gas in a 4,000 cm cube container. Okay, let this be my 4,000 cm cube container. The volume of this is 4,000 cm cube. Okay, 4,000 cm cube container. Exert a pressure of 1680 millimeter mercury. It means I have gases in here. And the gases bombard the walls of the vessels. Okay, a sample of gas in a 4,000 cm cube container exerts a pressure of 1680 millimeter mercury. It means the pressure here is 1680 millimeter mercury. Okay, at a temperature of 40 degrees Celsius. The temperature here is 40 degrees Celsius. Okay, if the quantity of gas in this container is reduced by 1/3, quantity of gas reduced by 1/3. Okay, calculate the pressure exerted by the remaining gas. Okay, pressure by the remaining gas is the question. Of course, in a question like this, we don't even have any need for this. We're basically talking about the amount of gas in here. Okay, let the amount of gas be. We're basically talking about the amount of gas in here. If the amount of gas had been reduced by 1/3, then what it means is that the remaining gas, the pressure they'll be able to exert, is not going to be up to the former pressure. If the amount of gas had reduced by 1/3, then the pressure exerted by the remaining gas is going to also mean the pressure of the former gas reduced by 1/3. So what this means here is very simple. If the quantity of gas had reduced by 1/3, then the pressure is also going to reduce by 1/3. So the new pressure now is going to be, what was the former pressure? 1680 minus, what is 1/3 of 1680? If the quantity of gas had been reduced by 1/3, then the pressure of the remaining gas is now going to be 1680 minus 1/3 of the 1680. So 1680 minus 560. Yes, 1680 minus 560 minus 560. So that's going to give us 1120 millimeter mercury. Very direct. So it is not true that at all time we have to say P1 V1 equals to P2 V2. No, it is not true that at all time we have to do that for Boyle's law. You simply flow with the question. In this particular question, the amount of gas had been reduced by 1/3. If that had been the case, then the pressure should also reduce by 1/3. The pressure before was 1680. So what is 1/3 of that pressure? Subtract it from 1680. This is going to be the remaining pressure, or the new pressure. Yes, moving on. The next thing is Charles' law. When we talk about Charles' law expresses volume and temperature relationship. Of course, keeping the other two variables constant. Not to forget that when we are describing a gas, volume, pressure, temperature, and the amount of gas are the four variables we use in describing the physical state of a gas. Talking about Charles' law. Charles' law states that the volume of a given mass of gas is directly proportional to the absolute temperature. Emphasis on the word absolute temperature, which we are going to talk about much later, provided the pressure remains constant. Here, volume is directly proportional to temperature. The implication of this is that when the volume increases, the pressure, when the volume increases, the temperature is also going to increase. When the volume decreases, the temperature is also going to decrease. So what you have here is that volume equals to kT. Of course, this proportionality sign becomes a constant, and this will mean V over T equals to K. In this case, the constant represents the number of moles of gas and the pressure that was constant. So what Charles' law is simply saying is that V1, since the quotient of the volume to the temperature is constant, it means V1 over T1 equals to V2 over T2. That is what Charles' law is telling us. It's telling us that when we increase the temperature of a given mass of gas, then the volume is also going to increase. And graphically, what this means is that you want to look at things this way. Of course, temperature in this regard, let's say in degree Celsius, okay? This is volume in cm cube. This is volume in cm cube, okay? If we increase this way, starting from the origin, of course, this is a direct proportion graph telling us that volume is directly proportional to temperature. If, for example, of course, when let's say volume is 10 cm cube, the temperature is about let's say 5 degrees Celsius. Of course, having both at the origin 0 here simply means something. It is telling us that when the temperature is 0 degrees Celsius, that the volume is going to be 0 cm cube, meaning that the gas ceases to exist. Meaning that the gas ceases to exist. Of course, this is, however, not true. This is not true simply because even when the temperature is 0, the gas is found to still have volume. Take for example, nitrogen. Even at minus 196 degrees Celsius, it still exists as a gas. So it is not true that when a gas is at 0 degrees Celsius, that the gas ceases to exist, or maybe the gas liquefy or solidify. That is not true. So usually when we talk about, okay, direct proportion, this is supposed to be the graph, but this is not true because even at 0 degrees Celsius, a gas is found to still exist as a gas, and at that point, it is not going to liquefy or solidify. So, owing to the fact that this is not true, that at a temperature of 0 degrees Celsius, it is not true that gas ceases to exist, or maybe they liquefy or solidify. The Kelvin scale was introduced, and it goes this way, that okay, it goes this way. Okay, this is temperature in degrees Celsius, and let this be volume in cm cube. Okay, what that means is that even at the temperature of 0 degrees Celsius, the gas was found to still have a volume. Okay, the gas was still found to have volume, so that if we continue to plot, if we continue to plot, we found that it is when the gas gets to minus 273 degrees Celsius that it looks as though the gas ceases to exist, as we have here. You can see the extrapolation here. You can see the extrapolation telling us that even when the temperature had fallen below 0 degrees Celsius, the gases still have volume. Take for instance here, let's say here, at the temperature of, at a negative temperature, the gases still have volume. Of course, till at least till about minus 273 degrees Celsius, it is at this point that the gas ceases to exist, and this temperature is what we call our absolute temperature. When we say absolute temperature, it is the temperature at which the volume of a gas becomes theoretically zero. That is, the gas liquefy or solidify, or simply, it is the temperature at which the gas cease to exist. So it's at minus 273 degrees Celsius, and that is what we call our absolute temperature. So how can we, make this graph, which is the graph of Charles' law, talking about absolute temperature? How can we make this graph, this minus 273, for example, become zero? And that is where the Kelvin scale comes into play. How do I make minus 273 become zero? That is, if I add 273 to this. Okay, imagine I'm adding 273 to minus 273 plus 273. That will give me zero. Okay, this is still my volume axis, and at this point I talk of another scale entirely, and that is the Kelvin scale. So if I add 273 to minus 273, it becomes zero, and I can then talk of, okay, volume being directly proportional to the absolute temperature. That is why we say absolute temperature, or what we call absolute zero, absolute temperature, is given a value of is minus 273 degrees Celsius or 0 Kelvin. Minus 273 degrees Celsius or 0 Kelvin. That is our absolute temperature. It is the temperature at which the volume of a gas becomes theoretically zero, or a gas ceases to exist. And for which reason, whenever we are dealing with calculations and we are given our temperature in degrees Celsius, we do convert it to temperature in Kelvin, and that will be temperature in degrees Celsius plus 273, so that we move from temperature in degrees Celsius to temperature in Kelvin. So that is that about absolute temperature. Absolute temperature is minus 273 degrees Celsius or 0 Kelvin, but invariably, Charles' law talks about volume temperature relationship, and it states that volume is directly proportional to temperature provided that the pressure remains constant. This is our graph for Charles's law, and that led to absolute temperature. Of course, we had to plot, and of course, this is the temperature at which the volume of a gas becomes theoretically zero, or is the temperature at which all of the gases liquefy or solidify, or we say a gas ceases to exist, and that ends that. So let's quickly take calculations related to Charles's law. Okay, moving on. Let's look at the very first question there. It states at 120 degrees Celsius, so that means that's T1, 120 degrees Celsius. A sample of helium gas occupies 180 cm cube. Okay, V1 equals to 180 cm cube. What will be the volume of the gas at 20 degrees Celsius? Okay, the new temperature is 20 degrees Celsius. If the pressure, what will be the volume? That's V2 is the question. If the pressure remains constant, of course, whenever we're dealing with temperature, we must always convert our temperature from degrees Celsius to absolute temperature. That's to the Kelvin scale. So this is going to be plus 273, and this is also going to be plus 273. Of course, this is going to give us a 120 plus 273. That will give you 393 Kelvin, and that's what we use in the calculation. This gives us 293 Kelvin. Okay, so we know that V1 over T1 equals to V2 over T2. So since we are looking for V2, this moves here. V1 T2 over T1 equals to V2. So that V2 equals to 180 times 393, 180, that's the V1 times T2, 293 divided by T1, which is 393. Okay, we're going to compute this, and that's going to give us 134.2 cm cube. Question 2, the initial volume of gas is 243, so V1 is 243 cm cube at a temperature of 15 degrees Celsius. T1 equals to 15 degrees Celsius. Okay, converting this is going to be plus 273, and that's going to be 288 Kelvin. Calculate its temperature when volume is 280. So I'm looking for the new temperature when the volume is 280 cm cube, pressure constant. Of course, looking at this, if the volume had increased from 243 to 280, I expect the temperature to increase correspondingly. So since I'm looking for T2, V1 over T1 equals to V2 over T2. So my V1 here is 243. My temperature here, T1 is 288, equals to my V2 is 280, and my T2 is the question. If this comes here, so T2 will be 280 times 288 divided by 243. So therefore, my T2 is going to be 331.9 cm cube. 331.9 cm cube. So that ends that on Charles's law. Now, moving on, let's quickly look at quantity volume relationship. Now, when we say quantity volume relationship, we're looking at Avogadro's law. Recall that these are the 4 parameters we are using in describing the behavior of gases. So Avogadro's law expresses the relationship between number of moles of gas and the volume of the gas. According to Avogadro's law, equal volume of all gases at the same temperature and pressure contains same number of molecules. Equal volume will contain same number of molecules. That is what Avogadro is saying. In other words, you know, when you say the number of molecules here, you're referring to number of moles. So what Avogadro's law is saying here is that volume is directly proportional to the number of molecules directly. If the volume increases, if the volume of a gas increases, the more the particles of gases you're going to have there. When I say the particles of gases here, I mean the number of molecules of gas. But the thing is this, when the volumes of gases are equal, then you expect them to contain same number of molecules. Thus, the volume is in proportion to the number of molecules of gases present. In other words, volume is highly proportional to N. So that it means V equals to Kn. What that means is that V over N equals to constant. So it means the quotient of the volume of a gas to the number of molecules is always a constant. Graphically, this is what that means. V in cm cube, number of molecules of gas, it's a direct proportion. And what this means is V1 over N1 equals to V2 over N2. Okay, more specifically, let us assume that, okay, we have 25 cm cube of let's say propane C3H8 contains let's say 1.01 times 10 raised to the power 23. If I have 25 cm cube of another gas, let's say sulfur 4 oxide, since the volume here, the volumes here are the same, I expect them to contain same number of molecules. Now let's assume I have another gas, and let's say the gas here is 50 cm cube of hydrogen gas. So the number of molecules this will contain is going to be in proportion to the number of molecules that 25 cm cube contains. If 25 cm cube contains this, if the volume has doubled, then the number of molecules here will double, and this is going to be 2.02 times 10 raised to power 23 molecules. Let's say the number of molecules now is 100 cm cube and has increased by a factor of 4. I expect the number of molecules here, let's say I'm talking about carbon dioxide gas here, I expect the number of molecules of the gas to increase also by a factor of 4. This is going to be 4.04 times 10 raised to power 23 molecules. So invariably, what we're saying is that when volume increases, number of molecules of gas is going to increase. If volume decreases, then the number of molecules here is going to also decrease. So that is that about Avogadro's law. Equal volume of all gases contain same number of molecules provided that the temperature remains constant. Let's quickly look at some calculations here. First question states, what is the number of molecules in 40 cm cube of oxygen? We're looking at what is the number of molecules in 40 cm cube of oxygen. 40 cm cube. Number of molecules is the question. What is the number of molecules in 40 cm cube of oxygen? If 40 cm cube of nitrogen, okay, volume of nitrogen gas here is 40 cm cube, and at that point the number of molecules here is 3.01 times 10 raised to power 23 molecules. Okay, looking at the question, what is the number of molecules in 40 cm cube of oxygen? I have 40 cm cube of nitrogen to contain this. So if the volume of oxygen here is 40 cm cube, just applying Avogadro's law directly, the number of molecules of oxygen here is going to also be 3.01 times 10 raised to power 23 molecules. It's a very simple and direct stuff. If the volumes are the same, then the number of molecules they will contain will also be the same. But if you're not content with that, then you can go, okay, volume number, you can go like volume of oxygen divided by number of moles of oxygen equals to volume of nitrogen divided by number of moles of nitrogen. Of course, what this means invariably is volume of oxygen here is 40, number of molecules of oxygen is what you're looking for, volume of nitrogen is 40, number of molecules here is 3.01 times 10 raised to power 23. Of course, number of molecules of oxygen here will mean 40 times 3.01 times 10 raised to power 23 divided by 40. So 40 cancels 40. Number of molecules of oxygen is still 3.01 times 10 raised to power 23. That is how it works. But the thing is even very direct. Without this, if the volumes are the same, then the number of molecules containing here should also be the same. That is what Avogadro's law is about. Moving on to the second question. Calculate the number of molecules in 100 cm cube of CO. Calculate the number of molecules in 100 cm cube of CO. Okay, talking about carbon dioxide, volume of carbon dioxide there is 100 cm cube, and I want to know the number of molecules that is there. If 25 cm cube of carbon dioxide, okay, I'm talking about volume of carbon dioxide here, contains 25 cm, okay, 25 cm cube of carbon dioxide contains number of molecules of carbon dioxide in this volume is 1.01, you see, 1.01 times 10 raised to power 23. That is what we have here. So when you look at this, if the volume, this is 25 cm cube, if the volume had increased by a factor of 4, I expect the number of molecules to increase by a factor of 4. So if I am to write an exam and I have a question like this, I'm not even going to waste time. The volume here is 25 cm cube and it contains 1.01 times 10 raised to power 23. If the volume had increased by a factor of 4, I expect the number of molecules to also increase by a factor of 4. But better still, I can still use this volume of CO over number of molecules of CO, volume of carbon dioxide CO2 divided by number of molecules of carbon dioxide. This is 100. I am looking for the number of molecules of carbon dioxide. This is 25 cm cube divided by 1.01 times 10 raised to power 23. Of course, this will come here, this will move here. So Number of molecules of CO will be 100 times 1.01 times 10 raised to the power 23 divided by 25. Year 1, year 4, you see, it's going to increase by a factor of 4. So what I'm going to have is 4.04 times 10 raised to the power 23 molecules. That is going to be the number of molecules of CO. Moving on to the third question, we have a question here. If 0.30 gram sample of hydrogen gas, in this case, we basically have hydrogen gas, okay? 0.30 gram, okay, we have the mass to be 0.30 gram. Sample of hydrogen gas has the same volume, okay, as another same volume as 9.6 gram of another gas S. Okay, we're talking of gas X here. Okay, the mass here is 9.6 gram, and you said 0.30 gram of hydrogen gas has the same volume as 9.6 gram of gas X. So you're telling me volume of hydrogen gas here is equal to the volume of another gas S. So if the volumes are the same, then the number of molecules they contain, normally the number of molecules here should be equal to the number of molecules of X. That is according to Avogadro'S law. If the volume here, it says, has the same volume as this. So if the volumes are the same, then the number of molecules should be the same. But that, by the way, so what this means is this. I'm talking about hydrogen. We all know that hydrogen equals to 1, talking about the relative atomic mass. But since hydrogen exists as H2, that's going to be 1 times 2. Okay, so the mole of hydrogen here is actually 0.30. That's mole equals to mass over molar mass. Recall that 0.30 divided by 2. The mole here is going to be what? 0.15 mole. Okay, if the number of molecules are the same, it simply means the number of mole is the same. If number of molecules are the same, number of moles will be the same. So since the volumes are equal, then the number of molecules there will be equal, then the number of moles will also be the same. So if I've gotten the mole of hydrogen here, then it means that the mole of X is also going to be what? 0.15 mole. So that I have interpreted. So I was told here, calculate the amount in mole and molar mass of X. So this is the amount in mole of X. And if you're telling me to calculate the molar mass of X, recall that mole equals to mass over molar mass. So molar mass of S is going to be mass over mole. So what this means is 9.6 divided by 0.15, and this is going to give us 64 gram. Of course, that is the molar mass of gas X, and that's looking more like SO2, because it's SO2 that has a relative molecular mass of 64. Look at the question very well. 0.30 gram of sample of hydrogen gas has the same volume as 9.6 gram, and that is where the point is, the same volume. If the volumes are the same, then the number of molecules they must contain must be the same. If the number of molecules are the same, it means the number of mole is the same. So I was able to get, since they mentioned hydrogen, I was able to calculate the mole of hydrogen. Calculating the mole of hydrogen, that means that is also the mole of gas S. So I've gotten that, and it's very easy for me to get the molecular mass or molar mass of gas X. And that ends that. And with that, we've come to the end of the first part, talking about gas law, Boyle's law, Charles' law, and of course, Avogadro's law. So that ends that. Subsequently, we move into general gas equation, ideal gas equation, and the likes. Don't forget, this is the channel to be to ace your next exam. Hit the subscribe button, share with your friend, and turn on the notification bell. For myself and the entire team here, it's bye for now.